All right, so C3, the question is, what is the color of the light emitted by the ChemCam laser, right? So if we're looking at it and we read the problem, we can see that the wavelength of the light that's used, right, is 1067 nanometers, right? So the visible region is from 400 nanometers, right? That's where like purple and violet and stuff is, up to 700 nanometers, which is where red is. And so anything that's higher in wavelength than red is typically referred to as the infrared region, right? And so that's, more in the near IR region. Anything that's below, 400 nanometers, initially is all going to be referred to as the ultraviolet region, right? And so that you can't see those. And so in this case right here, right, the light that's emitted is in the infrared region. Right? And so then what's the energy of the light emitted? So we can use the equation E is equal to hc over lambda. And so we can just plug in the wavelength that we have here. So we have h, which is 6.626 times 10 to the negative 34 joule seconds times the speed of light, which is 2.9979 times 10 to the 8th meters per second, over the wavelength, which is 1067 nanometers, right? And so because nanometers and meters don't directly cancel out, we have to just throw in the conversion factor, right? So that's 1 times 10 to the negative 9 meters per nanometer, right? Because now meters cancel, nanometers cancel, seconds cancel, so we only end up with joules. So if we plug that into our calculator, 6.626 times 10 to the negative 34 times 2.9979 times 10 to the 8th divided by 1067 times 10 to the negative 9th, you get 1.862 times 10 to the negative 19 joules, right? Which I think is what I have. Yeah, 1.86 times 10 to the negative 19. Right, so that's how you calculate the energy of that light. All right. Part C, right? So now here, part C of the problem lists the elements identified in the soil sample. All you have to do for this is just simply look at, the spectrum that was collected by the Curiosity rover, right? So you have iron, you have manganese, right? So you have, I'll just go through, right? So you have iron, you have magnesium, so Mg, you have silicon, Si, you have aluminum, right? You have calcium, titanium, you have aluminum again, you have calcium again, you have manganese, you have iron again, silicon again, calcium again, you have sodium, you have silicon again, you have hydrogen, right? You have carbon, there's lithium, potassium, oxygen, sodium again, oxygen again, right? So those are all the different elements that they found within the soil sample, right? And so that's how, when you read about or you hear about like, oh, all these different things were discovered on Mars or like far distant places, right? It's spectroscopy that's actually allowing us to identify those because, different elements have very characteristic spectroscopic properties. And so, based off of, where we see absorption, values or, specific absorption patterns tell us then like, okay, right, like this element is present or, this compound is present too, right? So, depending on how intense the laser is actually can allow you for actually to see what kind of compounds there are. Because, each compound has its own, spectral properties and everything as well. So, right. So that's how, people are able to, figure out like, oh, you have hydrogen, you have carbon, you have, oxygen, like, oh, it's a really rich soil with all of these different elements, right? It's through, spectroscopy essentially, right? Doing some type of, absorption, collection or emission collection. And so now part D, what are the three wavelengths at which silicon emits light in this sample? What are the energies of these transitions, right? So if we look at it, silicon, there's one that comes in at 288 nanometers, right? We have another one that comes in at like 414. And then we have another one at 642. And so the way to approach this, right, to calculate the energies of those transitions, you just simply have E is equal to HC over lambda. So if we plug in the values, we have 6.626 times 10 to the negative 34 joule seconds times speed of light, which is 2.9979 times 10 to the 8th meters per second over the wavelength, which, we'll just do the first one, 288 nanometers. So we have to make sure that we convert that into, meters so that everything cancels out. So we multiply this by 1 times 10 to the negative 9 meters per nanometer, right? So nanometers cancel, meters cancel, seconds cancel. We only end up with joules. So we plug this in, 0.626 10 to the negative 34 times 2.9979 times 10 to the 8th divided by 288 times 10 to the negative 9. So we get 6.897 times 10 to the negative 19 joules. Right, which is pretty much what I have right here, right? So I have 6.90 times 10 to the negative 19 joules. So, right, so that's the approach that you would use right there for that in those cases, right? And so you can do the same thing for 414 and 642 nanometers.